Okay, so also from us, a very warm welcome, especially to Andrew Duchowski. We have somehow here now the third time a bit of a spot into eye tracking, which is very interesting for all of us, I think, and the field is growing and we are all very happy. And Andrew Duchowski is for sure one of the most prominent in our field. He's the founder of ACM-ETRA, the one and only conference on eye tracking in research and in applications. But in fact, he's a professor of computer science. And he's not only interested in eye tracking, but especially in its relation to human vision and perception, and this requires to do some computer vision, computer graphics, and so on. He has a lot of publications, honors, awards, and I won't spend the time here adding them all to the list because I'm very curious and happy to hear and learn a bit more about real-time eye tracking today, its applications, analytics, and implementation. Andrew, it's up to you.
All right, thanks a lot. Happy to be here. Nice to see many faces. So this is, my understanding is it's kind of a discussion here, and so I don't have a talk that is full of fantastic results or anything like that. It's mainly kind of a review, and then it's me thinking about real-time eye tracking and where we need to go from here, sort of thing. So it's something I'm currently working on as we speak, as it were. So let me get going. I just start up another computer so I can see what it looks like over there to the audience. So let me share my screen, and hopefully if I do all that thing and then play this, we should be able to see everything, hopefully. Yeah, perfect. Okay, so this is me from a few years ago. This is on my boat on our lake that's over here, and I was trying to do some eye tracking to see how it would work. But for those of you familiar with eye tracking, you would kind of recognize this as almost a futile attempt because it works with infrared light illuminating the eyes. And so in a nice sunny day like this, that's particularly difficult. And so it didn't quite work anyway, but it was worth a try. So this is one of these eye trackers that's a mobile eye tracker made by Ergoneers called the Duchowski. So anyway, just before I start, some acknowledgement. Some funding I get from NSF. Sometimes NVIDIA throws in a graphics card. I've done some collaboration with SWPS in Poland and Tübingen. In Poland, I work with these people, including Krzyś Krates, among others. He is my, shall I say, current biostatistician. It's a label that we've given him. I was writing a grant, and the reviewer said, "You need a biostatistician." And I said, "Well, here's Krzyś, she's my biostatistician." Nina Gerer was helped me with some of the face stuff that we did, and she and I have taught tutorials at ETRA for a number of years, which we hope to do again pretty well for 2022. By the way, ETRA deadline is coming up November 29th. If anybody's working on eye tracking papers, wants to submit a full paper, please do so. I am working on one myself, sort of related to this talk. So the abstract I'll skip, it's already online there. This was me. The reason I have the 3 flags there is because I am actually of 3 nationalities: Polish, Canadian, American. So here's my taxonomy of gaze-based interaction, and I've been happy to add the left branch to this. When I started in eye tracking many years ago, the bread and butter was diagnostic, and so that is recording eye movements offline usually. and then doing analysis to find out where people looked, how long the fixations were, where the areas of interest or AOIs were, that sort of thing. And it's still one of the key applications, let's say, and uses of eye tracking, and oftentimes for assessment of things like interfaces, interface design, and training. So for example, a really big area is novice experts looking at chest x-rays. But in this talk, I'll skip the diagnostic part because I want to focus on the interactive real-time ideas. So we have assistive, active, passive, and expressive, and I will show you what these look like in turn. But before I do, what's happening right now, what's interesting, or rather recently, let's say last couple of years, and what's really fascinating is that in the span of about 3 months, a couple of years ago now, a couple of companies kind of ceased to exist just overnight. For example, SMI was bought by Apple, and suddenly SMI no longer exists. I know of several locations that were full of SMI eye trackers, like 20 eye trackers, the whole lab, and suddenly they lost support. On the one hand, it's good because, you know, the big companies are getting involved in this. Facebook, for example, owns Oculus, and so they are providing quite the impetus in VR at present. You know, the bad side is, of course, that these companies kind of don't exist. Like iTribe was a great idea. iTribe was, I used to have their eye tracker somewhere. It's this little tiny thing for $100. And so it was a really good thing. But anyway, so right now, eye tracking in VR happens to be a very popular thing. And so again, this is real-time eye tracking in the helmet and also in AR. $600, right? Notice the dollar figure. So you can get something like this fairly affordable. The one I have behind me on my desk there is a HTC Vive Pro Eye. Okay, it's a little more expensive, $1,500. But still, in 2000, you'll see the one I had was custom built for $60,000. And you can see in the picture, 2 infrared LEDs that were kind of handmade by Ricky Rasden at iScan. Took him a few months to build this thing, but it worked. And we got a fair amount of preliminary work in VR done back then. These days, it's off the shelf, so it's very nice, very cool. So who else is left today? We have wearable trackers. That's one class, let's say. Tobii, Pupil Labs, Ergoneers make them. Meanwhile, there's also the desktop variant that sits under a laptop, or I mean a display rather, or on a laptop. And Gaze Point 3 is a very popular one. I have a lab full of these things, actually a classroom with 20 of those. They're fairly affordable. You can get one, I think they were for around $1,000, depends on whether you get the software or not. Tobii provides a few of these, and of course, sort of the big research one is SR Research because it'll sample up to 2000 hertz. So that's sort of what's around. Plus, the latest things that we saw at ETRA demoed were these Pupil Labs Invisible glasses on the bottom right that look like glasses, don't require calibration anymore, and you just put them on and there's an eye tracker in there, which is really, really cool. On the left is Sophie Stelmach at Microsoft, who was instrumental in building the HoloLens 2, which is an augmented reality helmet-mounted display with eye tracking built in. So that's kind of what the state of the art is, as far as I know at present, that is driving the current research. So a few basic slides for the uninitiated, let's say. Your vision, human vision, its highest acuity is only about the size of your thumbnail at arm's length. Outside of that, your acuity drops off drastically. 10 degrees, it's pretty much down to 50%. And so that really is the reason why your eyes move, because you want to pick up high detail at the next location that you're interested in. or that attracts your attention. So the eye movement types that we have are the very fast ones. These ocular muscles are the fastest in your body, and they execute saccades. And so the fast movements of the eyes from point to point, and these happen to be one of the easiest ones to pick up in real time or offline, because they're just an edge in time. And so they're fairly easy to detect. But then again, as you'll see later in the talk, there are some issues with this. Smooth pursuits are when you're tracking an object, that's basically constant velocity. And then there's also what you would find in the helmet, vestibulo-ocular response. And that is if you're looking at something and your brain knows you want to keep looking at the thing, and it knows you're rotating your head because of the semicircular canals in your ears, it'll counter-rotate the eyeballs to hold gaze fixed. In VR, you also have vergence, so your eyes move in and out. And all these types of eye movements, I don't think we have a very good handle on doing or detecting all of them at once in real time. And that's really something that's been kind of bugging me as of late. Fixations are what we're mostly interested in, because that's when visual attention is, let's say, most active. But it's a bit of a misnomer, because here you got tremor, drift, and microsaccade. So the picture here from Pritchard is showing what the eyes are doing over top of the photoreceptor mosaic in your retina. And so you see the squiggly, the jittery lines are the tremor. If you plot them over these sort of curves, that's the drift. And then if your gaze drifts off target, you would issue a microsaccade back to center. And so you could also wonder about detecting those in real time if you're so curious. Anyhow, this is also a fantastic paper and a YouTube video I recommend from 91. Carver Mead did the time derivative silicon retina, where he devised a camera that functioned as your eyes would, which showed to demonstrate that if you hold your gaze steady, everything disappears, which was a fascinating piece of video and really nice kind of demo of this. All right, so let me quickly go through these before I get to the real-time aspect. So active is classic human-computer interaction dating back to Jacob, who found that everything you looked at would get selected, which was not what you wanted. So that's the minus touch problem. And he suggested dwell time if we just do a little timeout per item to affect selection. And that's been in use since 1990. It's still in use today if you want to do real-time selection. Here's what it looks like on the left. If I'm clicking on 9610, you will see that I have to dwell a little bit over the 9. Actually, to start, you have to do the start button there. 9, 6, there's a blink here. You saw that blink coming, which interferes with the data. And then we had to have an end of text kind of issued here when we were doing dwell time. Of course, for real time, you don't have to use dwell time if you don't want to. And one way to get around that is with gestures, but those apply to very kind of specific interface design. So here, same number, 9610, but we're only looking at the boundary crossing. So 9610, and it's really fast. At the top is what you see, the real-time output of this, and you'll see that we've got a little bit of ambiguity when the gaze grazed over the 7 and 6. And so my student there at the time said, well, we can just weight the selection based on the latter items that you touched with your eyes. So gestures are also very popular in real-time eye movement analysis, but I won't really go into that today. So just an idea of where they get used and why is VR popular all over again. Well, of course, you want to shoot at stuff, select things, pretty basic things, games, of course, and I have a bunch, but I'll skip. So in the interest of time. So selection active is you want to click on something. Passive, on the other hand, which is where I'm at here, is foveated rendering or gaze contingent displays. And this is Oculus. So this is Facebook basically saying that This is going to be core technology. This was 5 years ago, so maybe it is now, who knows. Anyway, the point being also was that at one point, Zuckerberg was asked, is Facebook interested in eye tracking? And he said no. But owning Oculus, of course they are. So they do care about eye tracking. And so what is foveated rendering? This is from computer graphics. If you look at something like we have in the upper left image, well, we just need to give you high detail there. On the left, low detail. So that is real-time manipulation of geometry and pixels, not necessarily gaze, but it's in response to gaze. So you have to know whether you're fixating or not. And so the idea here for computer graphics is that you want to speed up the rendering. And so these guys said, yeah, we can hypothetically do this 100 times faster. In general, you could apply this to simulation of scotoma, which are things like age-related macular degeneration. So this is a simulation of what you would see if you have this problem. The AMD is when your photoreceptors basically start to fail. And oftentimes it is right in the middle of gaze where you don't want it. So it's a real problem. We did a short paper for Eurographics where we tested that with a fuzzy spot in a gaze contingent way, and people hated it, of course, but that was the point. So it's annoying, and people that are actually afflicted with this have to learn to look off the fovea like astronomers do when they look at faint stars. You can also manipulate color and temporal information using eye trackers. So that's kind of where you're manipulating a display. Expressive, let me show you a little bit of this. This comes from the film industry and avatars. And so we want to animate eyes. So on the right there, we've got stop motion animation from Tootly Pootly, where it was just a doll animated. And then they cut out using something like, rendering the fake eyes and put in real eyes, which was really effective. Bottom left is the robot from Rogue One, my favorite Star Wars movie, and it was really done really well. You could see he had little saccades, and it was quite effective. Upper left is Beowulf, which shows a really bad example if you do eyes poorly. Same with bottom right, the Polar Express, and those were critics lambasted that effect, saying that the avatars look kind of dead and unconvincing. Meanwhile, in real principal photography, when you take a shot of a real person, they do sometimes, for effect, zoom in on the real eye, like in the center from a movie called Limitless, which is a kind of a reaction shot that they use of the person that the main character is talking to. This is from Kick-Ass 2. It only lasts 1 second. So when I play this, you will see the reaction. The actor here is reacting to kind of a stimulant drug, adrenaline of some sort, and you'll see the reaction here. 3, 2, 1. It's just 1 second, and it's obviously fake, but you can see that it's quite effective. And how do you do this in real time with graphics such that you don't fall into the uncanny valley where things look unbelievable? So that's the application that we're talking about here. So it's really eye movement animation, and it's used in games to show off whether these characters are trustworthy or not. Like this kind of an older work now, even older work dating back to 2003, which basically said the more convincing your avatar is, like here they were rather basic, but still, the more elaborate the gaze should be, the animation of gaze. Here's 2013, a cheap way to implement this. The avatar is simply looking at you as you rotate your head, and it looks pretty decent. So this was Borland's wife that did this. I happened to talk to her at some conference I was at, and she goes, "Oh yeah." She sent me this video. I think it was quite good. So an easy effect, I'll play this from Toby.
Feels a little bit right. Like,
I don't know if the audio is coming through.
So if you look to your right, on the right side, this is the same avatar with eye tracking enabled. So what you can do is you can look around. You can try to wink, maybe close one eye.
It's really cool.
Yeah. This is very good. This is very powerful in social games. Like if you meet another player online, you use your eyes to give life to your avatar.
I had another demo from Toby, so that's why I have that. I still don't get paid by Toby at the bottom there. But you can see the idea. If you don't want to animate the eyes procedurally, you can use the eye tracker inside the helmet to get the position of the eye and then transfer that to the avatar, and it looks better than not doing anything. But even with that, the eyes are rather noisy, or the signal you get from the eye tracker. I should say the other way. I should say the eye tracker is noisy, not the eyes. And so if you use the signal verbatim, the eyes will do all sorts of crazy things. I think the eye tracker tends to amplify the jitter that's there, which is kind of strange. But you do have to worry about that. And so there's an amount of signal processing that you want to do in that instance. All right, assistive is one other thing where I'm just getting involved in, and that is looking at subtitles in VR. And so this is something we're just working on right now. And here, as you may imagine, we're interested in whether you're actually reading the subtitles or not. And for the moment, right now, it's diagnostic. So we want to just record this, play it back. But you can do this in real time too. It's kind of interesting that the HTC Vive, the eye tracker works at 120 hertz, the display at 90. And so you have to do a little bit of multi-threading to get the fast rate for the eye tracker. But here's what it looks like. And you can do this in real time. But so when it turns blue, it's a fixation. When it's red, it's a saccade. But here lies the problem. So, and it just occurred to me very recently when we looked at the data that got recorded. And from a signal analysis perspective, okay, the eyes are doing huge jumps in small amount of time. So velocity is high. And so we were labeling them as saccades, but they're not really saccades. I don't know what that is, to be honest. But if you look at the actual recorded time, the saccades are way too long than what they should be. And so here we've got a problem in terms of real-time eye movement analysis that I thought my filter that I've often used in diagnostic offline approaches, which work really well and does work really well, here would be no problem. But it fails to do something appropriate right here when the eyes do these huge jumps. I don't know how to do that just yet. I don't know how to handle this. And if anybody has any ideas in the discussion, let me know. I have some ideas of my own, but as yet they're untested. All right, so real-time tracking, what I did in offline is usually what happens offline is you get eye movements on the monitor, right, 2D. And so you could filter them with a Butterworth filter, which I tried years ago, but I actually stopped because if you over smooth the data, you will lose some of the high frequency stuff which you need. And so what I usually use these days is the Savitsky-Golay filter. It comes from it's an old filter. It's very very handy. It does smoothing before it differentiates, which is nice. So you want a little bit of smoothing, but not too much. And so if you use the Savitsky-Golay, you don't need the Butterworth anymore. And then it's a matter of simple velocity thresholding to get the saccades over fixations. And so here, if we plot some offline things, okay, here's what gaze data looks like, and you and I can tell, oh yeah, those little clumps are fixations. And so you can get this really excellent book, Holos and Holos Digital Filters, really good. That's where the equation up there comes from. That's from the Butterworth, which we don't actually need. the smoothing part. So if we substitute the Savitsky-Golay for the G, that's all you need to get at the velocity of gaze data in real time or offline, doesn't matter. And then you will get fixations out of it. But here's the key thing. Offline, for table mounted trackers, usually the head is fixed, right? There is no massive rotation of the head that you get in VR, for example. Other kinds of eye movements that I'm interested in besides fixations and saccades are these things, focal and ambient. They come by various names. They are scrutinizing and skimming, things like this. And here's one way to get them. So if you look at the K coefficient from my biostatistician, Dr. Kreitz over there in Poland, he came up with this where he says the first part, fixation duration minus saccade amplitude. So if you're fixating for a long time, big number minus a subsequent saccade that's very small, big number minus small number, you get a big K, and that's focal viewing. And if we draw the focal fixations with a darker hue, you can see the focal fixation in the graph below. If you have a small fixation, like a short duration followed by a big saccade, like you see at the beginning there, then you have a small number minus big number, and you get an ambient kind of fixation. You may ask yourself, well, that doesn't make sense because you've got duration, time, minus amplitude, distance. How can you take this subtraction of two different units? You can't. So if you take the z-scores of both, so you need the mean and standard deviation, then you can. So that's what Krzyś came up with. And so we've got this, I guess it's a dimensionless unit for K that just is either 0 or above 0 or below 0. All right, so those are the kinds of things I'm interested in. Now let's go to the real-time stuff. What can we implement in real time? We can do saccade detection, sure. And getting those, you can, anything not a saccade, you can call a fixation. What about ambient focal fixations? Can we do those in real time? That remains to be seen. Smooth pursuit detection. Here's the thing. We've been doing eye tracking for many, many years, decades, and I do not yet know of a good event detector that will classify saccades, fixations, and smooth pursuits all at once, believe it or not. The so-called ternary eye movement analysis kind of filter. I don't think maybe it's that difficult. It's just that I haven't seen one that seems to work very well and is kind of nice to implement. I looked at the Kalman filter at one point and kind of got there, but not quite. And so that kind of fell by the wayside. On top of that, can we do K? Maybe. But what I've seen from smooth pursuits is the orbits interface. So that is a series of papers. I think Andreas Bulling is instrumental in that. And then also, most recently, I've been asked, I have a couple of papers on cognitive load from pupil diameter using wavelets. And so people are asking me, hey, can you do this in real time? And so I'm like, I don't know. So event detection is deceptively easy. Here's the filter up there is very short. Savitsky-Golay filter. It's only 5 or 7 values in there, and they're fixed. So it's a finite impulse response filter. It's very short. You can clearly implement that in real time. But I think it misses the pursuits, like I showed you in the video of VR. The other approach is the IDT, or position variance method, and I had some code in C++ years ago that purported to do this. And so that one basically says, well, the gaze points have to be clustered within an area. So that's already one one threshold that you have to have, and over some minimum and maximum duration. So now you've got up to 3 possibly variables that you have to worry about and set possibly per person to do the position variance scheme to detect fixations. The Savitsky Golay is the opposite. It's the velocity-based filter. So we're just looking for saccades, which are easy, but then what you get might not necessarily be a fixation. So I don't know. Now I'm rethinking that clustering and duration thresholds may yet be useful. And I really like this paper from ETRA, I think 2014, which was by Douglas DeCarlo and Santella, I think, on the mean shift. That one was also offline, really elegant to implement. And I don't know whether you can implement a mean shift in real time. I mean, there would only be one mean that you're shifting all the time or resetting. So maybe. So here's what I was thinking. Real-time event detection to me is kind of like this. Velocity is bigger than threshold, or velocity is less than threshold. Simple enough. And that works. But what about pursuits? Can we stick pursuits in there? Maybe it's just a matter of using some kind of a dual threshold. If you're really fast, it's a saccade. If you're close to 0, it's a fixation. And in between, it's something in between. You're a pursuit. You're doing a pursuit. And so here, okay, it's added complication of 2 thresholds, but maybe it's not so bad. And maybe it'll work. Let's see if I can quickly do a demo here for you. Let's see what this looks like. If I do that, let's see if this shows up. So here, this is how that might work in real time. Let's see, I just got to remember. You can test all this stuff with the mouse, by the way. It's a cheap simulator of eye movements. Here's a fixation, saccade. Actually, here's saccade and so forth. So if I go to full screen and then sorry, but I have to calibrate the eye tracker. So this is all real-time Python code that talks to the gaze point, which is sitting there running on my Windows laptop. And so here is real-time eye movement analysis. We can turn off Butterworth filtering for display purposes, and you can see that the gaze is kind of jagged with sharp edges. If I turn the Butterworth filter on, oh, it looks nice and smooth. We can't really use that except for visualization. But then here's the key thing here. If I'm fixating something, that should be blue. If I make a quick jump, that should be red. And then anything in between, if I'm doing maybe kind of a pursuit motion, it should be yellow. And so maybe this works. I don't know. Blinks are probably going to be red because they get registered as fast kind of eye movements. Now, the other issue here is if I can hold my gaze steady, what you'll see there, it's hard to see, but in the middle there is a little box. There it is. If I do slight drift, this is work in progress. I haven't got all the bugs out of this yet, but the little box there, it's hard to do. You're getting sort of this biofeedback. The little box, if you can see it, is the runtime mean. And so that would affect the K coefficient down here at the bottom right. I can't look at this and try this at the same time, but hopefully right now K should be big, but I don't think, actually I turned off K calculation here. But the point is, if I'm doing a long fixation with very small saccades, K should be big here. And if I do huge jumps, K should be small. So in this code, because it's kind of work in progress, I haven't really turned on the K, or actually broke my code from before. But these are some of the issues that are coming up in terms of real-time eye movement classification. So that's what this was based on, and how well it works, I don't know yet. I have to run a study and actually do some testing with this. But The K coefficient, I think, is doable in real time if you look at computation. Really what it depends on is the mean and standard deviation, right, of the most recent run of fixation, what the most recent fixation duration was, and the last saccade. So we should be able to get that based on running average and running variance. And if you look at Welford's online algorithm, it looks kind of like this, mu being the mean. It actually works quite nicely. I've been using this for many years. I just recently put in the standard deviation thing, and that seems to be working okay. And that would just feed into the mu up top there of the durations and amplitudes. So that's kind of what I'm working on at the moment with this. I put in pursuits because my last ETRA paper was sort of on that. And here it's a slightly different problem, the way the orbits interface works. So here you're looking at a target that moves in the circle. And the idea was, if I have, let's say two targets, one that goes this way and one that goes the other way, right? Let's say you're selecting something. So can you use pursuits to select? This is going back to the old Midas touch problem. And here, yeah, you can do these phase kinds of classifications. So if we just compare phase and amplitude, you can compute tangential error, the TE, which is how far away are we from where the target is, and then what distance away from it. And then you know which direction you're going. And so again, you can compute velocity of target, velocity of gaze point. Which one was which here? I think gaze point was the gray one, the G, and the target was the red one. Doesn't really matter. But here, the orbits interface, which Bulling, I think, used to great effect, a couple of Chi papers, worked on that, but not necessarily detecting smooth pursuits. It was just, which direction are you going? Good enough. I know which circle you're targeting. Now, so cognitive load. If I didn't go over this, but if you look at my couple of last Chi papers, it started with the IPA, and they were both wavelet based. And then it didn't seem to work when we moved the target off axis. So then we came up with the LH IPA and the LIPA, which did kind of a low to high frequency ratio. So here, the numerator up top there is the low frequency of the wavelet, and then the denominator should be the high frequency. And low to high, they may have gotten this backwards in this particular slide. Yeah, I think I may have gotten it backwards. Should be flipped. So in wavelet space, it's a pyramidal transform of the pupil diameter, right? So here we're always looking at a 1D signal. And the idea is if your pupil oscillates quickly, then it's high cognitive load. So the theory goes. And so that's what Marshall suggested years ago. And so here, if you take wavelet analysis, the top low level, or depending on how you look at the pyramid, is the high frequency component. And so the high frequency component, if you now take the low frequency component, the one in the middle of the pyramid, L over H would give you the ratio. And so you'd have to look at the middle of the pyramid to get the low frequency component and then divide by the high frequency component. And that seemed to work offline. So how do you get this to work in real time? And I don't have a good answer for this, but my hypothesis is that wavelets probably won't work because you still need a fairly long sample of the signal, like, 2 seconds worth or something, so that you can get at the multiple layers of resolution. And so I thought, why not go back to the Savitsky-Golay filter, which you can tune. And so you can have a Savitsky-Golay filter that will look for high frequencies and ones that will look for low frequencies. And will that work? So I don't know, but that's what I'm looking at the moment to see if we could do something in real time. And so here's an example of the, if I play this, it's not a very good example, but the pupil diameter signal is the bottom line. And so here it's scaled to fit in. And so you can see that what we want to see there is this high frequency oscillation. Okay, so if we apply one of the filters to it, you would get the yellow line. If you get the low frequency filter, you get the bottom line. So is this low frequency over high frequency? And if you do the ratio, you get the red line. And then what do you do with that? So you have to do some kind of thresholding, maybe something like this. And if you do various wavelet-like things to this, you might get this kind of threshold blip that adapts to the modulus maxima of the signal, and maybe that'll get us someplace. So I don't know. That's what I'm working on at present. And so we'll see. I'm not yet convinced that this works. It might be a step in the right direction. Actually, what I would really need is somebody who is really good at digital filter design. And so that's where I'll leave you some questions to ponder, how to get things to work in real time. How I came to this is really from kind of the graphics perspective, because I had this book on my shelf here. I don't know if I can find it. Oh yeah. So in computer graphics, it was sort of the same thing. There was a book called Real-Time Rendering, and I always kind of thought about this. What's the big deal? But it is a big deal, because the problem is for real-time rendering, and real-time eye tracking, you have a budget. You have only a certain amount of time that you can work with to get a response. And so wavelets kind of need a long time to get the pupillometric measures. So how can we do this in real time? Finding saccades, I think, is easy, but then you might miss out the other things. For example, at the Duchowski seminar we were at just a few years ago, somebody came up with the question of, well, how do we detect glances? We all kind of went, well, that should be easy. But a glance is a quick look at something where you actually see whatever is there. So you perceive it quickly enough. But you only need a small amount of time to do it. And most filters right now, like the Savitsky-Golay, would probably consider that to be a blink or some errant piece of something or other. It'll throw it out. Off we go. So there actually isn't a good glance detector that I know of. And to combine it with everything else, I think that's the kind of question that I've been thinking about recently. Okay, so open up for the discussion. We got a few minutes. Please, I'll welcome any questions or anything you might want to say to me. You're a fool. This paper here from 2 years ago has all the answers. If you have that, tell me. I'll be happy to read it.
Yeah, thank you, Andrew, for this fascinating talk. I really loved the presentation, especially the boat in the beginning. I think it's a fun experiment to try eye tracking on a boat, and it's also fascinating that you showed this live demo and the videos from your ongoing work. As you said, we have now time for questions. So if you have a question, you can raise your hand, or you can write your question in the chat. And while you're thinking about your questions, I can start with the first question. Or Jan has a question. Jan, you can go first.
Okay, yeah, thank you so much, Andrew. This was fascinating. Thanks really for sharing this. Zoom is a blessing in a way. Like we get to hear from people like you that we wouldn't probably otherwise have been able to fly over here. So
yeah, but I missed out on the beer afterwards,
I know. I'm sorry about that. So the first thing is, I'm almost embarrassed to ask this question because it sounds like such a commonplace thing to say. But you were mentioning that you were struggling with, for example, the question of how to do a real-time ternary filter that was able to also, get these pursuits in addition to fixations and saccades. And it looked to me like one of those problems where, and now comes the word, machine learning should be, I was surprised that you didn't mention it. I would really love to know, have you looked at it and it doesn't work, or is it something that still has potential that needs to be explored more deeply, or has AI ML not gotten there yet? So I could see like supervised learning working there, where you tell the system this is pursuit and this is this, and then the system goes
definitely
ahead and finds these things.
Personally, I think, first of all, I have to admit that I don't know ML or AI very well. Unfortunately, that was one of the classes I didn't take as an undergrad, and I am now very upset about this, and I haven't had time to actually go back and revisit. But what I understand about AI is it could, on the one hand, be perfect for this, because at the core, I think it's a classifier, right? I mean, it's what AI really does is classify things based on learning of some sort. And so it goes back to I have an old book from Duda and Hart on pattern recognition, and it's kind of along those lines. So oftentimes in AI, the first thing you see is K means classification, blah, blah, blah. And okay, so yes, I think that AI ML is probably almost perfect for this, if not being too huge of a hammer. On the one hand, the problem seems deceptively simple. You should be able to say three thresholds and you're done, and it should just work. And so I don't know if you even need to do learning, because saccade detection, we get that pretty easily. And so adding pursuits to it should be bloody easy.
Yeah, it sounds like it could be really tempting to go maybe even down the unsupervised route, where you say, well, so here's all the data we have, and we're not quite sure yet. Apparently, the simple filter mechanisms don't seem to quite grasp the problem in the right way. So if you threw unsupervised learning at it and just let it figure out its own rules in a black box way, which is sort of like the modern AI approach, rather than the traditional sort of white box, I put up a bunch of rules thing, then it could end up finding ways of differentiating these things to your, in a way that you like. Of course, the price that we then pay is that we don't really know how it's doing it, right? That's the uncomfortable part of it. But I just heard from people who were doing, language translation, that years ago, there was like this professor who had been slaving away at finding a good, translator program, and then an undergrad just walked in and installed, basically TensorFlow, and just blew all his profs, earlier work out of the water, because the system was just able to latch onto patterns that they had never thought about modeling because they weren't aware of them.
Yeah, that'd be great. If you know of anybody, or you have a student that can walk in and show me this, I would be happy to use it.
Yeah, so unfortunately, I think AI machine learning experts right now are in somewhat of high demand among research colleagues, and we find that ourselves, our colleagues in AI get just hammered with requests, because everybody's trying to get to grips with these new tools that are now out there that we should just, I guess, all of us learn how to use as part of our work, I suppose. I don't know.
Yeah, I definitely think there's potential for it. Certainly, I'd be a fool to discount it and basically say, "Oh no, it'll never work." Of course, it could work. Yeah, sure.
Yeah,
I do like the explicit sort of, here's what it should be, though. I want to know this, and I should know this, But So far, when doing things on the display and offline for so many years, the Savitsky-Golay saccade detectors worked so well, and I haven't really had occasion to bother. And then in VR, now I'm moving my head around, it's like, oh, damn, it ain't working like it used to. So
yep.
Everything old is new again, which is okay, because it'll again make us think about the age-old problem. I mean, 20 years ago, it was, how do we get fixations, And so now it's just another way to look at it. It's the old problem has reared its head again, which is fine.
I'd love to follow this up with a nerdy question, if I may.
Sure.
We've been doing some work in for example, using iPhones to use their like gaze estimation that they do, and like a couple of our papers recently at Kai were about things like using the user's head movement in relation to their smartphone to determine gestures and things like that. And that seems to work well. But I would like to know, have you been able to hook any of the high-end eye tracking systems, the current ones, up to a Mac natively, or are you going the route of pain, which is through a local network and then getting the data off some Windows machine that's slaving away in the corner?
Yeah, there it is, right there, the Windows machine. Yeah, so I'm using Gaze Point because it's affordable, like I said. But yeah, I had to go through the pain of writing the networking code to get the data out of it. Yeah, I don't know what's on the Mac. Good question. Nothing that I know of. I keep asking Craig Hennessy, the guy who builds these things, I say, when are you going to port your thing to the Mac? Oh, but I do have something, not real time, but for any kinds of offline stuff, the latest versions of CyclePy actually have code built in that talks to GazePoint, Toby, and SR Research iLink. So that guy's name is Sol Simpson. He wrote that backend called IO Hub, and I haven't tested it, but in principle, he's got the networking code in there. So if I fired up CyclePy here and design a little experiment, in principle, it should work. I haven't had an occasion to test it yet, but yeah. So CyclePy would be a nice tool for doing experiments, and actually, they've got a demo that uses real-time areas of interest. And the demo is such that they make you look up here and you have to gaze there for the thing to disappear. And then another one shows up. So they actually do have a real-time demo in there that you could try, and it ought to work over the network. So give it a shot. Let me know how it works.
Thanks.
Anke?
Yeah, I'm taking all my courage now as a psychologist and ask for these machine learning stuff. So as far as I understand, all our attempts, what we aim at is going mobile with all our devices. This means in the wild, but also in VR. But these machine learning algorithms, they require so much computing power. So do we have to take this all with us and when we are moving around, or will it be leaner when we understood it at some point? Or?
No, so my understanding of it, which is limited, but the compute power kind of comes up front. And oftentimes what I've seen is that where the compute power and the bulk of stuff comes in is in training, right? So in the end, it ends up being kind of like this, let me just say, for the sake of analogy, it's just a filter with some coefficients. And the key is to get the right coefficients. And so you have to train this stupid thing on, 100,000 samples of whatever, of thing that's true positive, false negative, or true negative, things like that. And then after you've got that, it's gone and given you the filter that you want. And so now I think in principle, you should really use that thing, which is the lightweight piece at the end, but I could be totally wrong, but that's my understanding of it.
But then it can never adapt.
Well, then you have to have some kind of these supervised, unsupervised tidbits that add to this. But that's not for me to answer. That's for an AI ML expert. But I mean, the People Lab's invisible. That thing has got machine learning in there, which works so that you don't have to calibrate the tracker anymore. And that is based on machine learning. How they did it, I don't know. But at ETRA, they said through the magic of machine learning, and that's all they tell you.
Susanne?
Yeah, thank you very much. Very exciting. As we are here in this area of pervasive computing environments, I was wondering where we stand with eye tracking, like in fully natural environments. If you think of, I would like to switch on a lamp or reduce the volume of my TV, and then my fixations, the saccade, everything is in very different depth So
Yeah.
where are we in regard with real-time eye tracking when it comes to a varying depth of where I look at?
Yeah, so that you can look up Rule Vertigal's papers from years ago on what did he call it? Attentive user interaction or interfaces or something. And so that was kind of like, and I think he even started a company called Zook, X-U-U-K. I don't know if it exists or not, but his idea was that the devices would have eye trackers that were sort of bigger versions of this thing, the gaze point that I'm using. And the one he had from Zook was this, if you can imagine, it was a box full of LEDs that would just shoot out huge cone of LED light, and then it would detect your gaze. So the TV would know you're looking at it. That's the point. So that's if you embed these sensors on the devices, that's potentially one way to go. Another way to go is if you're actually wearing the tracker. And then what I do in the lab, because I don't know, I'm either lazy or stupid or both, I attach these things everywhere, you know. But eventually these will go away. What's nice about these is that they give you position and orientation. So, you know, it's nice that you can get a little bit of geometry out of this. But again, AI or ML, you'll be able to recognize that, oh, I'm looking at the TV set because that's what a TV set looks like, you know, something like that. So I bet you AI and ML will eventually do away with these, and you could do pattern recognition on stuff that we're looking at, you know, in the visual scene. The HoloLens, for example, does something fascinating. When you first turn it on, it goes and maps the environment. Like it actually, like behind your screensaver is full of these triangles, right? And that's exactly what you see when you turn the HoloLens on. It maps surfaces onto things it sees, onto planes that it sees, and then you can sort of interact with these planes. It's fascinating. Plus, it's got the eye tracker inside. So my students in the lab, the first thing they did was download a game where these bugs crawl out of the wall, and you look at them and shoot at them. And so there's an example of kind of a pervasive application in a helmet-mounted display.
And how much do you think the content will actually influence the results in the eye tracking and what I can guess from it? Like if I have a TV and something is shown on it, then of course the smooth pursuit and other effects will become in place. So if I have a red lamp in my living room, it might also have some bottom-up maybe effects on my eye tracking. Do you have any experiences on that?
No, but you're definitely asking the right kinds of questions. And yeah, bottom up versus top down, right? So yeah, a lot of work from IDI and company, of course, did the bottom up stuff, but then how do you get intent? That's another question. How do you know what the person is actually trying to do? And so I think here you're going to need some kind of higher level metrics besides fixations, like the ambient focal stuff that'll give you a bit more. And beyond that, I'm sure there'll be even other things that are going to be context dependent. I think I've come across papers that try to kind of put together the bottom up versus top down to try to sort of bridge that gap to figure out what it is you're trying to do. But I think user intent was definitely a topic that came up at the Dogstill seminar we had a few years ago. Yeah, very good question. Many directions that can go.
Okay, thank you.
Marian?
Yeah, thank you. I was wondering, since you mentioned your 20 computer gaze point lab, whether you thought about the scalability of some of these eye tracking procedures you mentioned. For example, just measuring fixation. Have you thought about measuring eye tracking from like 20 persons at the same time, possibly even in real time?
I've thought about it. I just don't have the time to do it. But yeah, and actually there's a company out there called Reali.io, and they are doing eye tracking through webcams. And as you imagine, it's very difficult because you've got the additional complexity of different screens, different dimensions, different lighting conditions, people at different distances to the camera, all sorts of problems. And because it's poor resolution compared to an eye tracker, I think they had to have very many calibration dots on the screen to make it work. But yeah, it's another question. If you can do that via webcam, why not do something that you're measuring eye movements from many people at the same time? Some really simple example of this would be some kind of game, you know, where there's tons of, I'll go back to Anka, the psychologist, and there must be tons of games where you have people are either working in a cooperative mode to do something where you could use eye movements to do it, or you could do a competitive mode. You know, you're trying to make sure that the other guy doesn't get to where I'm going, something. So you could probably devise some interesting games that you could use the eyes for. And if you did that, that'd be a really neat kind of application, possibly in real time for multiple eye tracking users at the same time.
Yeah, sounds like a great idea, definitely. Yeah.
Yeah, I've thought about it, but no time to implement.
Okay, maybe a last question from my side, because we have to look at the time as well. So Andrew, you spoke about that it's possible to generate real-time eye visualizations, or the eye movement visualizations which look like real eyes basically, and also about the importance of eye contact in our interpersonal communication, for instance. And something which annoys me sometimes is that in video conferences like this one, people don't pay attention to what's being said, and that they look at their emails or something like that. So I'm wondering whether there is potential for like deep fake eye visualizations, where I'm in a meeting and I'm reading my emails, but I'm perceived as somebody who's paying attention to.
One of my colleagues, there's a system you can buy. It's free, OBS, and it's sort of like Zoom on steroids. And what you do is you set up multiple video feeds, right? And then you basically click on, I want that feed to be acting as the camera. And so he's got videos that he's got kind of like this, you know, looping, and then he goes off somewhere and he's not even there. So,
but do you think there's potential for something in between where kind of where I'm being recorded and my eye movements are being kind of deep faked in a certain way? And
definitely,
okay,
yeah,
good.
yeah. I think you can. I'm still amazed that, you know, I'm happy that Zoom works nicely and everything, but this eye contact in teleconferencing is a really old problem that's never been sufficiently well addressed. I think the deep fakes, the eyes, you could just redirect the eyes a little bit, and you would get pretty far with it. And you know, it goes back to Hiroshi Ishii's Teamwork Station from, like, I don't know when it was, 1990s or something. But that teleconferencing and eye movements and eye contact has never been really very well or satisfactorily done. And here we are, you know, in Zoom, and the problem is still there. You know, if I look at people who have their cameras on, everybody's looking, you know, at the screen, not at the camera.
Yeah.
So definitely it's something that should be done. Oh, here we go. Somebody's got the FaceTime eye contact correction feature. There you go. So actually it should be here, right? Because I already have iOS 15.
Okay.
Does it work? Anybody try it?
Well, yep. They're actually correcting. So if you're looking at your screen slightly below the camera, they're helping you to make it look as if you were looking at the camera by literally doing what Enrico was suggesting, slightly modifying the displayed image of yourself to look as if you were looking at the camera rather than down at your screen. So it's almost there.
Oh, fantastic. I knew somebody would do it sooner or later.
But then we need an extension so that it follows maybe the gestures of the speaker or the slides being shown and something like that. So
yeah, you might end up with something creepy, like, you know, they're always doing this VOR thing, which isn't the case.
Okay, so unfortunately the time is already up, so we're already 7 minutes over our time budget. So Andrew, thanks again for this really fascinating talk. That was really nice to have you here for this series.
Hey, my pleasure. Thanks everybody for showing up. Appreciate the audience. Thank you very much. It was fun.